All right, so we'll talk Monte Carlo integration, and then all right. So we left off on Monday's lecture talking about applications of Monte Carlo integration, and we started off here. We said with Monte Carlo integration, we can estimate the integral of any function. This is kind of I guess maybe like the origin of this thing is that if you want to estimate some kind of function like this, right? You want to estimate the integral of some function h, but you don't know how to integrate this directly. What can we do, right? So, because there's a lot of integrals that we can't integrate directly. There's no closed form solution, and there's like, I've forgotten how to do all of those integral tricks. You know, there's all sorts of different tricks you can do to try to figure out the solution for an integral, but in some cases it's still really hard to complete the integral, right? So what we can do is we can take advantage of this fact. We can say that, you know, if you say what's the average value of the function on some interval, the average value of the function is going to be equal to the integral divided by the width of the interval, right? So we can just take this. This is the integral that we want to know. And if we take the that integral and we divide by the width of the interval, b minus a, then that's going to give us the average value of the function x, of h of x on that interval, okay? And this function, or this thing, 1 over b minus a, if I bring that inside, okay, if I bring the 1 over b minus a on the inside, we can say, hey, that is equal to f of x, okay? F of x, we can say is the PDF of a uniform distribution is going to be 1 over b minus a, right? So, you know, uniform distribution, the PDF says all the values are equally likely, you know, that interval width is b minus a, so that it integrates to 1. So anyway, this thing can be written as this integral here, the integral of h of x times f of x, okay? And, you know, from Monte Carlo integration back in like Monday's lecture, we said, you know, that's equal to the expectation of h of x, okay? This integral is equal to the expectation of h of x, okay, where x is a random variable with this PDF of f, okay? So that means if we can generate x from the uniform distribution, which is going to have this PDF f, which is 1 over b minus a, then we can calculate the expectation of this by taking kind of the sample mean, h bar sub n. And the value of the original integral then, if you want the original integral, which is just this part, all you do is you just multiply it by the constant b minus a. Okay, so this integral can be approximated using b minus a times h bar of n. Okay, so that's what we have. And so just to kind of write out the steps, we're going to estimate, oops, this should be estimate I. Sorry, that's a typo. Estimate I as follows. We'll estimate the expected value using this, and then we can estimate I by taking this and multiplying it by b minus a, right? And here, all of these values are just coming from uniform. So if you have the uniform distribution from a to b, you just generate x, x1, x2, x, whatever, x through n, compute h of x, and then and take the sample mean of all of those values. Okay. All right, so far so good. I feel like this is okay. I guess let me go ahead and give you your first quiz answer. First quiz answer for today is D as in dog. D as in dog. It's going to be your first quiz answer. And then, okay. All right, so we can take a look at this function. We're going to say h is equal to the quantity cosine 50x plus sine 20x, and then you add those two together and you square that, okay? So we have cosine 50x, sine 20x quantity squared, and we're just going to evaluate it on the interval 0 to 1, okay? But we could have chosen a wider interval if we wanted to. Just kind of following the example in the book, that example starts off going from 0 to 1. Okay, so if you solve it analytically, we can ask Wolfram Alpha to do it. The true answer is around 0.9652. Okay, 0.9652. And so this is what it would look like if I try to input this into the computer. All right, so here I just create a sequence from 0 to 1. Okay, increment by 1,000ths. And then I got cosine of 50 times x plus sine of 20 times x. I'm going to take that quantity and I'm going to square it. And that's going to be my function h. Okay, so h is a function of x, where I plug this in. All right, and so here's the plot. Okay, and then the estimate of the integral is rather straightforward. We generate a bunch of values. So here I'm going to generate n. N is going to be set to 100,000 here. So I'm going to say generate 100,000 uniform random values on the interval 0 to 1. And that's going to give me a vector x of 100,000 values. And then I compute h of x. So I'm going to just compute that function, the value of the function for those 100,000 values. And that's going to give me another vector, h underscore x, okay? And then I can just ask, what's the mean of h underscore x? And the value I get is 0.96686, okay? And that's kind of close. The true value is 0.9652, and I'm getting 0.9668, okay? 0.96686. So, you know, I'm off by a little bit. I'm off by about 2/10 of a percentage point. Okay, about 2/10 of a percentage point. The integral is going to be b minus a times h bar n. Okay, b minus a is 1, so that just ends up being h bar. So this ends up being the same. But yeah, if I had a wider interval, if I generated values on a interval greater than 0 to 1, I would just multiply that by the width of the interval there. Okay. All right, I'm gonna do a little bit more here, okay? And so what I want to do is I want to create a plot. Okay, we're going to create a plot of how h bar sub n, how this estimate changes as my n increases. Okay, and to get this estimate, I did 100,000. That's a little bit too many for this graph here, so I'm going to just kind of reduce it to 10,000. I'm not going to recalculate any of these. So this h underscore x is still a vector of 100,000, but I'm only going to look at basically 1 through n, okay, which will be the first 10,000 values. And here I'm going to get the cumulative sum, and then I'm going to divide by this vector 1 through n here. Okay, so so I'm going to get basically a vector of a running mean. Okay, so it's going to start off, you know, what is the mean after 1 observation? What's the mean after 2 observations? What's the mean after 3 observations? And so on and so forth. And then eventually it'll be what's the mean after 100 observations? What's the mean after 101 observation? What's the mean after 1,000 observations? What's the mean after 10,000 observations? Okay, and so this will kind of give me a running mean by giving me a cumulative sum. So we say cumulative sum, and then we're going to divide by the vector 1 through n. So this will just give me a running mean or a cumulative mean. Okay, and then I want to be able to estimate the variance of this. Okay, and so if we go back to Monday's lecture, we said, you know, what's the variance of h bar sub n? and then we went through a bit of math, and we said the variance of h bar sub n, it's basically a sample mean, and so the variance is going to be 1 over n times the variance of h of x. All right. Well, what's the variance of h of x? Okay. Well, we can do some manipulation, and basically it comes down to saying the estimate of the variance of h of x is going to be this quantity, and therefore the variance of h bar sub n is going to be estimated by this. It's going to be 1 over n squared times the sum of h of xj minus h bar sub n. Okay, and so this is going to be our estimate of the variance of h bar sub n. Okay, so this is coming from Monday's lecture, the work for calculating the variance of h bar sub n. So I'm not going to redo this here, but that's what this is referring to. So if you're wondering where did this thing come from, because it looks a little bit wonky, take a look at slide 27 of Monday's lecture, and that hopefully that will explain how this is done. Okay, and then I've configured this. And I used the letter M here, but maybe I should have used the letter J because that's what appears in these slides. What we're going to do is we're going to calculate basically the running variance. So it's going to be the variance for the first M terms. So because I could get this easily if I just pick a number, but we can just say, you know, what if I want to do it for the first 100 terms or the first 200 or the first 1,000 or things like that. And so the estimate of the variance is going to be basically the sum of, and then all of this here, and it's going to be each value 1 through m. So like if I did the first 100 values of h of x, which is this part, h of x sub j for whatever j values you have, minus h bar sub n of and that's kind of the running h bar value, so the 100th running h bar value or whatever. We're going to take that difference, we're going to square that, and then and sum everything up, and then we're going to divide by however many values I have, in this case m squared, okay, which is what we have here. So this is going to be kind of the running variance. So in the beginning, my variances will be very big because I only have a few observations being used to calculate it. And then as we gather more and more data, my variance value is going to get smaller and smaller as my m gets larger and larger. Okay, and so in order to kind of compute that for all of our things, I'm going to run and apply, and we're going to apply it to the values basically 1 through 10,000, and we're going to apply this function variance underscore m. Okay, and then so that will give me an estimate of the variance. And now I'm going to take the square root of that to get the estimate of the standard error. Okay, question says, how does the cum-sum function, cumulative sum function, relate to the formula for the variance estimate? This one, so this is going to be the cumulative sum, which is going to be useful for calculating the running mean. So it's going to be like the mean based on the first 100 values, or the mean based on the first 200 values, or the mean based on the first 300 values. Okay, and what I want to do is I want to be able to estimate this variance. And so in order to do this, basically rather than resampling every single time, I just did all of my sampling in the beginning, and then I'm going to kind of go back, like quote back in time, and just say like, what is my estimate of h bar sub n if I'm only looking at the first 200 values? What's the estimate of h bar sub n if I'm only looking at the first 300 values? And so this is going to be basically h bar sub n, and then I'm looking at the mth value, because this thing is actually a vector of what is h bar sub n for the first 100 values, first 101, 102, all the way up to the first 10,000 values here. And so we're going to just pull that one out. And so the cumulative sum function gets used in calculating kind of all of those running mean values. So I hope that helps. All right. Yes, so it's because I want to change m. Yes, it's because I want to be able to calculate what is the estimate of h bar. What is this estimate if I only if I calculated it based off 100 values, or if I calculated it off of 1,000 values. So, because I want to see how H bar shifts over time as I gather more and more observations. And as H bar shifts, then my variance of H bar is also going to shift as I gather more and more observations. So I kind of have a function to calculate the variance of this thing based off of, M observations. Okay, and so basically what we're going to see is that in the beginning, the standard error is huge. And then as time goes on, the standard error is going to get smaller and smaller and smaller. So that's what we're going to see in the graph. Okay, so here I get the standard error by taking the square root of the variance estimate. And then when I plot it, I can kind of plot the running mean, the H bar value. Okay, and so that's going to kind of wobble quite a bit. And then as time goes on, as we gather more observations, it's going to kind of steady and level off because of the law of large numbers, saying that as n gets larger, it's going to get closer and closer to the expected value. And because I have a standard error now, I can create kind of confidence intervals, okay? And so I can be 95% confident that the true value that we're trying to estimate, that is, this quantity. So, H bar is basically a sample mean where the true value is the expected value of H, okay? And we can be confident, wherever my sample mean is, I can be confident that the true value is within, 2 standard errors or 1.96 standard errors of this, okay? And so, so I'm going to kind of create confidence bands going up 1.96 standard errors and going down 1.96 standard errors. And so when I do that, this is kind of the graph that I get, okay? And so we see there's a lot of variance in the beginning. It's actually kind of hard to see, but if I zoomed in, these blue lines are very wide, and as time goes on, the kind of the width of the confidence bands shrink and shrink, and they get smaller. Okay, and from here on out, they're basically these 3 lines that just get the width of the confidence band just gets more and more narrow as your number of iterations increases. So this is going up to 10,000. I know for the original estimate, I pulled up 100,000, but if I graphed all 100,000, the plot gets really, really, really boring, because kind of the interesting stuff happens in the beginning, and then basically after about 3,000 and so on, you basically have these 3 almost parallel lines. They're not exactly parallel because as time goes on, they get closer and closer and closer and closer together. But basically, you just kind of have these 3 stripes, this blue, black, and blue stripe, kind of showing the confidence band here. All right, but yeah, the math does exist in order to kind of estimate the variance of your estimates of your kind of your Monte Carlo estimate here, and that's what we've done. Okay, is that all right? You feel okay about this? Okay, let me go ahead and give you your second quiz answer. Second quiz answer for today is C as in cat. C as in cat for the second quiz answer for today. All right, let's take a look at another example here. This is a little bit silly, but we have a function that can do what because it's silly because this function already exists, right? So let's say we want to estimate the normal CDF, the normal cumulative distribution function, okay? And this function already exists. We've got p norm on the computer. But I don't know if you knew, but p norm on the computer is technically an approximation. It's accurate to 16 digits, so that, on our computer where we're using floating point numbers, being accurate to 16, that's about the limit of floating point numbers anyway. So, So if p norm is accurate to 16 digits, that's fine. But if you needed something even more precise, more accurate than 16 digits, p norm is not going to be able to do it, okay? Because it's technically an approximation. Yeah, so I don't know, in the future, we might have computers that are more accurate than 16 digits. Like we might not use type double. We might, I don't know, type quadruple or something. And we'll have even more decimal places of precision. Who knows? But so even though p norm exists, we can still approach it as a Monte Carlo problem, and it's still kind of interesting here, okay? So the definition of the normal CDF, okay, the definition of really any cumulative distribution function is what's the probability that, your random variable is less than some number, right? So here it's for f of x, big F of x, it's the probability that z, a standard normal variable, is less than some value x, okay? And this is equal to basically, over here I've got the PDF of the normal, okay? This part's the PDF of the normal, and we want to integrate from negative infinity up to x, basically the PDF of the normal dt. So that's the definition. And this thing over here, this integral, has no closed form expression. Okay, so there's no closed form expression for this, and so so we can approximate this using Monte Carlo integration. Okay, yeah, p norm, just an approximation, but we can do this. All right, so what we're going to do is we're going to use the indicator function. Okay, the indicator function is basically ones and zeros. So you can almost think of it as the indicator function being like on the computer, if you have a logical vector, the indicator function would be like you convert the illogical into a numeric, right? You could do, if you do as.numeric or as.integer or as.double of a logical vector, that's basically the indicator function. It becomes a 1 if it's true, and it becomes a 0 if it's false, right? So you basically create a logical vector of z less than or equal to x, and it's going to become 1 if it's true, and it's going to become 0 if it's false. If it's going to be 0 if z is greater than x, right? And so the expected value of this indicator function is going to become 1 times the probability that z is less than or equal to x, plus 0 times the probability of this thing, that z is greater than 0. Oh, I'm sorry, this should be greater than x. That's a typo, I gotta fix that. Okay, so 1 times the probability that z is less than x, plus 0 times the probability that z is greater than x. Sorry, that's a typo there. Okay, and well, the 0 part goes away, and so your expected value is just going to be the probability that z is less than or equal to x. And well, what is that? The probability that z is less than or equal to x is exactly the definition of the normal cumulative distribution function. Okay, so we can take the normal cumulative distribution function and express it as the expectation. Okay, so the expectation of this indicator function is equal to the standard normal CDF. Okay, and so now that we've expressed this integral of interest, or express the function as an expectation, we can use the Monte Carlo estimator to estimate this function. Okay, and what we're going to do is we're going to let h of x be equal to the stuff inside the integral. Okay, and so basically using kind of what is Monte Carlo integration, we're going to say, well, our values come from a normal distribution, okay? And big F is going to be the expectation of this indicator function. So to estimate the normal CDF, we're going to just take z, we're going to generate a bunch of random values of z from the standard normal distribution. And then we're going to compute basically a numeric vector of whether this is true or false. Okay, it's going to be 1 if it's less than x, 0 if it's greater than x. Okay, so we're going to take kind of this comparison statement and turn it into ones and zeros. And then we're going to estimate it by taking the mean. Okay, basically the mean of that logical vector. And that's going to be our kind of our h bar sub n. And if you think about it, this is going to work as the cumulative distribution function for any random variable. Okay, as long as you're able to sample from this distribution, you can get the cumulative distribution function of any random variable. So, okay. And one thing to think about is that this random variable, this thing right here, the indicator as a random variable, that's basically a Bernoulli random variable. And the Bernoulli random variable is defined by the probability of success P. And so this is a Bernoulli random variable with success probability P equal to the probability that Z is less than or equal to X, which is basically our CDF, right? And so when we estimate this as basically a sample mean, this is basically the sample proportion of successes in n trials. Okay. So it feels a little silly, but if you think about what's basically happening is if somebody said, hey, I need you to tell me what's the probability, what's the CDF, what's the kind of cumulative probability that a normal value is less than 1.28, okay? One way we can do this is I can just generate okay? I can generate a lot of random normal values, right? And so here I've got our norm, and I said 10 to the 8th. So that's 100 million values. So I'm going to ask the computer to generate 100 million random normal variable values. All right. So that's a lot, and it takes the computer a little while to execute that. Okay, to generate 100 million values. And so let's say I want to estimate what's p norm of 1.28? Okay, the true value of p norm 1.28, the true value is 0.8997274. Okay, so right around 90%. It's a little bit less than that. Okay, and to estimate this, I'm going to take my 100 million values, and I'm going to just see what proportion is less than 1.28. Okay. So I just said Z less than 1.28, I get a logical vector of true falses. And then if I do what's the mean of a logical vector, it's going to give me the proportion with that property. Okay, so here I've got 0.8997519. Okay, so something close, but a little bit different from the true value. Okay, we can see, what's our estimate of p norm of negative 1.645, okay, and we get something just under 5%, 0.04998, whereas the true value of p norm negative 1.645 is just ever so slightly different, 0.0499891 versus our value 4998811. Okay, so we're getting, I would say, pretty good estimates of what the true value is. All right, and this is just relying on the fact that I've generated 100 million random values of Z. Okay, I've just generated 100 million random normal values, and I'm using that to estimate, the cumulative normal probability. Okay, p norm of 0 we know is exactly 0.5. We know exactly half of the normal distribution is less than 0. In 100 million, how many are less than 0? Okay, just our estimate is just ever so slightly off. Okay, the true value is exactly 0.5, and we're getting 0.49948. Okay, so something close to half, but it's not exactly that. This is an estimate. And it's basically the sample proportion that came in less than 0. And that's what we have here. And so what I can show is we can kind of create a table for how our estimates improve as I take more and more samples, okay? And so this I goes from 2 through 8, meaning we're going to look at 10 squared, 100 values, 10 cubed, 1,000, 10 to the 4, 10 to the 5, all the way up to 10 to the 8. So we're going to see how our estimates improve from using by powers of 10. So we're going to use 100 random values, 1,000 random values, 10,000, 100,000, a million, 10 million, or 100 million random values. And we're going to see how those estimates improve for different boundaries here, okay? So we're going to first do it for basically p norm of 0. We're going to look at the quantiles for 0.5, 0.75, 0.8, 0.9, 0.95, 9999, and 0.9999. Okay, so we're going to have all of these values. And so we've got kind of an inner loop and an outer loop. So first we're going to do it for with 100 values. Basically, what's the proportion, looking at just kind of the first 100 values of x, which is basically 100 million random normal values. What proportion is less than this boundary, this boundary, this boundary, all the way up to this boundary? And then we're going to do it again for when I equals 3, using the first 1,000 values, what proportion is less than the boundaries? And we're going to kind of fill out our matrix. And so here I filled this out. I added row names, and I also added one more row for the actual proportion. Okay, so the actual proportions are 0.5, 0.75, 0.8, 0.9, and so on and so forth. And these are the cutoff boundaries. Okay, for this is p norm of 0, p norm of 0.6745, 0.8416 will give you 80%. 1.2816 will give you 90%. 0.6449, so a little bit off from 1.645, will give you 95%, so on and so forth. Okay, and so at 100 values, we got 52%. With 1,000 values, we got 49%. With 10,000 values, we got 0.4992. And we can see that as the number of n increases from 10 to the 3rd, 4th, 5th, 6th, up to 10 to the 8th, we can see our estimates improve or get closer and closer to the actual probability here. Okay, so the true value is 0.75. And, by coincidence, we got 0.75 up here, but then, as we take more random samples, we're getting something close to, but not exactly 0.75. And the accuracy in general improves as we take more and more random values. Okay, now because it's random, it bounces around a little bit, but overall we can see the values in the 100 million row are a lot are generally closer to the true value than the values in, say, like the 10,000 values row. So okay, and so so there's kind of a question of how many values do we need to achieve a certain level of accuracy in our estimates, right? And so to kind of get an idea of that, we need to know, well, what's the variance of our estimate? And so our estimate, f hat, our estimate of the cumulative distribution function, in our case, we know is basically the sample proportion of successes in n Bernoulli trials, right? So this is basically the sample proportion. And so if you recall, back from stats 10, I think you guys learned that for a sample proportion, the variance is p times 1 minus p over n, or for the standard error of a sample proportion is the square root of p times 1 minus p over n, right? I think you guys learned that, or at least in 100B or 100A, you probably learned, the variance of of a sample proportion is this. And so, f hat is a sample proportion. And so the variance of f hat is going to be basically f hat times 1 minus f hat over n. Okay. And when you're talking about sample proportions, maximum variance occurs when that proportion is 0.5. And so if we're kind of taking a conservative estimate of the variance for, kind of overestimating the size of the variance, the variance can be estimated to be 1 over 4n, okay? Because if you plug in 0.5 for f hat, you're going to get 0.5 times basically 0.5, so that's going to be 0.25 divided by n, and so that's going to be 1 over 4n here. All right, and so if you take the square root of that, conservative estimate for the standard error is going to be 1 over 2 square root of n, okay? And so what does this tell us? This tells us that if we want to improve, how accurate our Monte Carlo estimate is, it improves, at a rate of 1 over the square root of n, okay? And I think this is something you learned in your intro stats class, is that if you want your standard error to cut down in half, your sample size needs to be 4 times as big. And if you want your standard error to be cut down to be 1/10 the size, if you want to reduce your standard error by a factor of 10, your sample size needs to go up by a factor of 100. Okay, and so, for example, if we want to be 95% confident that our estimate, our sample proportion, is accurate to 4 decimal places, then we want to make sure that basically 2 times your standard error is less than 1 decimal place, right? Or, is less than 10 to the negative 4, right? And so if you want to make sure that 2 standard errors is less than 10 to the negative 4, knowing that a standard error is 1/2 over the square root of n, you need n to be at least 10 to the 8. Okay, meaning that if you want to be accurate, if you want to be 95% confident that your sample proportion is accurate to 4 decimal places, you need to sample around 100 million values, which is a lot, okay? But this relationship of things converging at a rate of, 1 over square root of n, you can kind of look at this for any kind of other of these things, and that rate is going to hold true. Okay, is that all right? Do we feel okay about this? All right. So now I'm going to introduce this next topic, importance sampling. I'm going to just introduce the idea of it, and then we'll get into it on Friday. Okay, so you can start thinking about this. And then I'll probably release your, post your second homework assignment pretty soon. I know your first homework assignment is still open, and that's not due for a couple more days or a few more days. But I'll go ahead and post the second homework assignment now, in case you want to get started on it or look at it. And then I'll make it due. I'll make sure you guys have plenty of time to work on it as well. Okay, so so far we've been talking about Monte Carlo integration, and we said, if you want the expected value of this function h of x, where x comes from this PDF f, it's equal to this integral, and we can estimate it by taking random values of x from f and taking the sample mean of this function. Okay, but this depends on our ability to produce random samples from the PDF f of x. And so what do we do if we can't sample from f of x directly, right? So far, all of our problems, we've been able to, all of our functions have been basically probability distributions that were already built into R, right? So we've been using things like, I think our first example was the baseball example, where we drew samples from the beta distribution, and there's R beta inside R. We can also generate random values from the normal distribution, random values from the uniform distribution, and all of these kind of ordinary, quote, regular probability distributions are built into R. So we can generate values from the gamma, exponential, chi-squared, F, Poisson, binomial, T. There's a whole bunch of distributions, and we can generate random values from those things. But we might not always be able to have, or we might not always have a built-in random distribution function. And so what do we do if we can't draw random samples from f of x directly, right? So this is kind of the direction that we're going to head in. This is what we want to do. And so one option, and this is what we're going to look at next week, is we can talk about generating random values from different distributions. Okay, we can talk about generating, like if you have the PDF, okay, if you have the PDF, how can we generate random values from it? Okay, so that PDF might not be one of these nicely behaved PDFs, and we might not have a built-in function. Can we still generate values from that? We'll talk about that next week. Okay, can we generate random values from different distributions? Okay, and then the other option is we can perform importance sampling. Okay, we can perform importance sampling. All right, and so the idea behind importance sampling is that this is the thing you want to estimate. This method relies on being able to generate x from f. But here we're going to say, I don't know how to generate values from f. Okay, but I do know how to generate values from g. Okay, and g is just an entirely different distribution. So someone says, hey, I need you to generate some exponential values, or I need you to generate some random normal values. And you say, well, I don't know how to do that. I do know how to generate values from the gamma distribution or something like that. Okay, well, what do we do, right? Or somebody says, can you bake me a chocolate cake? And you say, well, I don't know how to make a chocolate cake. I know how to make, raspberry pie or something like that. And all we're going to do is we're going to just generate from a distribution that we do know how to generate values from. Okay, and the only requirement for this function g of x, this PDF, is that the support of f of x has to be fully contained in the support of g of x. Okay, so if f of x is defined on the interval 0 to infinity, then g of x needs to contain 0 to infinity. So you can use a function that's defined from 0 to infinity. You can use a function that's defined from negative infinity to positive infinity, but you're not allowed to use a function that goes from 0 to 100. Okay, because if f of x goes from 0 to infinity, it's not fully contained on the interval 0 to 100. So that's the only requirement, is that the support of f, that is the region where f of x is greater than 0, that region has to be fully contained in the support of g. Okay, and we'll go over this on Friday. But the idea here is that we currently have the expectation defined as this integral, h of x times f of x. And all I'm going to do is I'm going to take that and I'm going to multiply it by g of x divided by g of x, right? I can do this because this is basically 1. And so if I just rearrange things, then now I can group this. And basically, this is now just the integral of some function times a PDF dx. And this is for g of x, and so this is going to be the expectation of this function where x is defined by this PDF g. And we can do this. So this function over here is equivalent, or this expectation over here is equivalent to this expectation over here. Okay, and it's going to work as long as there's no spot where f of x is something greater than 0 and g of x is 0. Okay, and that's going to be fine because that's going to be our requirement here. Okay, so as long as g of x is not 0, where f of x is bigger than 0, there's no issue here. Okay, and so we'll take a look at this a little bit further on Friday. But that's where we'll end here for today. Let me give you the last quiz answer. Last quiz answer is E as in elephant. E as in elephant is your third quiz answer for today. Okay, E as an elephant. All right, so we'll end here for today, and we'll see you guys on Friday.